So this is it, we've made it. We're finally at the end of our series of videos on the P block elements and their compounds. And I realised that through the last 6 videos where we've looked at each of the groups from 13 to 18 individually, that it can seem overwhelming and like there's a vast amount of things to learn about all these different elements, and that it does just seem like lots of facts to learn and interesting snippets about element X or element Y, and that can be overwhelming. So I thought in this video I'd make a summary of what we've learned so far to really highlight some of the important phenomena and subjects we've touched that you can apply across the P block, so the trends, the periodicity, and things like oxidation states and bond enthalpies. So like the most important things that I think we need to know from the P block, and hopefully this will help, especially with revision, but also by cementing some of the things we've seen in the last 7 videos. So let's start by looking at some of the periodic trends of the P block, and we'll start with trends across a period. So this is at the top. I've got a general observation or trend that most P block elements can adopt more than one formal oxidation state. The only one really that you'll see with just one oxidation state is fluorine, which is always -1. But this is just a general observation. Now, with the help of my beautiful homemade periodic table highlighting the metals, metalloids and non-metals, let's look at some trends as we go from the left to the right, so across a period like this, and also the reasoning behind them. So the first trend is that metallic character decreases as we go from left to right as we go across a period, and the reason for this is that the ionization increases. So metals usually have low ionization energies, so as we go across and the ionization energy increases, they become less metallic. The maximum oxidation state increases, and this is because the number of valence electrons increase. So oxidation, if you remember this oil rig thing, oxidation is loss of electrons. So the more valence electrons there are, the more there are to lose. So the maximum oxidation state increases. The ionic character of oxides and halides decreases, and this is because as we go across the period, the electronegativity increases. And that means the gap in electronegativity between the element and the oxygen or halogen will be smaller, so it will be more covalent. So you remember ionic structures have big differences in electronegativity and covalent ones have smaller. And finally, the acidic character of oxides increases. And this is again because the electronegativity increases. And I think we'll see on the next slide again that it's the more electropositive metals form alkaline oxides. So as we're going across and the electronegativity is increasing, the acidity of the oxide increases also. So this now is the periodicity going down a group, again with this wonderful homemade periodic table, and this time the colours are highlighting the basicity of the oxides, like we were talking in that last point as well on the last slide. So the first trend is that the metallic character increases down a group. And the reason for this is the ionization energy decreases. So it's exactly opposite to the first point when we were going across a period. Then we have the lower oxidation states as we go down a group. And this is due to the inert pair effect, something that I will touch on in a few slides. And this is the statement that an oxidation state too lower than the maximum is more stable towards the bottom of a group. The AX, where X is non-metal, bond enthalpies decrease as we go down the group, and this is because the atomic radii increase. We talked about this in quite a lot of the videos. So for example, carbon with the halogens, the bond enthalpy of the carbon-halogen bond goes down as we go down the halogen group because these get larger and there's less overlap of the orbitals then, and the bonding isn't so strong. And finally, the oxides become more basic as we go down a group, the opposite of what we saw in the last point on the last slide, that they become more acidic going across a period, and this is because electronegativity decreases. And we can see here that as we go down a group, so the green squares are acidic oxides, purple amphoteric and red basic. And we can see at the top they're all acidic, and then as we go down they become more purple and red, more amphoteric, basic. And although we're applying this to the P block, it's true for the whole periodic table. So if we throw the S block on the side of it, like this, we can see that you've still got this general pattern that in the bottom left of the periodic table, the oxides are more basic, and this is because they're more electropositive. Then as we go up through the periodic table, like up and right, so an increasing electronegativity, we see that we go from basic oxides through amphoteric oxides and towards acidic oxides. So really correlated with the acidity of oxides and electronegativity. We've talked a lot in these lectures, and not just the P block ones, but the ones preceding it as well, about oxidation states. And it's just more complicated in the P block, so I think it's important here to summarise it and how to calculate them. And I've got here my 10 rules for calculating oxidation states. And yeah, it's wrong to say they're my 10 rules. I didn't invent them. If you Google rules for calculating oxidation states, these 10s will appear on Google as well. But yeah, if you want an example of me going through these in more detail, if you look at the worked answers for the questions from the last lecture, so lecture 6, there's the first question actually. I apply these 10 rules to calculate the oxidation states in 6 different compounds. But let's quickly go through the 10 rules of calculating them now as well. So first one is cation first, anion second. If you go back and look at the halogens with oxygen, those bonds, we saw a nice example of that. So the example was when it makes oxygen bonds with fluorine, you get OF2, whereas if it does it with chlorine, you get Cl2O. And this is because the positively charged thing, the cation, is always first and the anion is always second. That's really helpful for you knowing which has lost an electron and therefore been oxidized, got a positive oxidation state, and which has gained an electron, therefore been reduced and got that negative oxidation state. A free element is always 0. So this can be anything if it's an inert gas, just something like Ar, monoatomic. Nitrogen as an element, so N2, this is also 0. So if it's just the element as a free element, oxidation state is always 0. Single atom ions are equal to the charge. So like H plus, for example, the charge is plus, therefore the oxidation state of the H is +1. Same with O2 minus, the oxide anion. The oxidation state of this oxygen then is -2 because it's equal to the charge. Hydrogen, the hydridic hydrogens, so this is when hydrogen is more electronegative than what it's bonded to, is in a -1 oxidation state, and a protic hydrogen, when hydrogen is bonded to something more electronegative than itself, is in +1 oxidation state. Oxygen itself, usually -2. It's a really nice place to start off when you're working out oxidation states. If there's not hydrogen involved, look at the oxygen, it's usually -2, but exceptions apply. Rules 6 and 7 are really nice. Group 1 is +1, group 2 is +2, and this is, yeah, pretty hard and fast. You'll be struggling to find one where they don't apply. Rule 8 is that group 7 is -1. For fluorine, this is absolutely 100% of the time true. For the other halogens, that can change. So we've got an example up here again of chlorine actually being a +1 when it's bonded to the oxygen. And for the interhalogen compounds that we looked at, I remember I said, yeah, interhalogens are very interesting because you can see all the oxidation states when they bond to each other. So again, exceptions apply, but a really good rule to stick to help work them out. Neutral compounds add up to 0. So with something like H2O, we know that this is all the oxidation states are going to add up to 0. If we follow the other rules, hydrogen is +1 because it's protic, oxygen's -2, which follows rule 5. Very nice. And then finally, polyatomic ions, add up to the charge. So things like OH minus, the hydroxide anion, we know that the oxidation states of the oxygen and the hydrogen in this case have to add up to -1. So then still the same oxidation states as we saw in water. Oxygen is -2 and the hydrogen is +1, and that adds up to -1. In the group 13 video, I was talking about the Lewis acidity of boron halogen compounds, and how as we go down the halogens, the Lewis acidity increases. And what's the reason for this trend? And it was all to do with something called p-pi bonding and how that stabilizes geometric changes. So I've got 6 bullet points here that kind of take you through, if this was a question, how to answer it. So the first one is that forming an adduct with a Lewis base causes a geometry change from planar to tetrahedral. So the BF3 itself has this trigonal planar structure, geometry, which is shown here. And then if it was to form an adduct with a Lewis base, could just be like another fluoride ion, could be something like a water with a lone pair from the oxygen, or pyridine, I think we saw in the textbook as well. Then the geometry changes from this trigonal planar to tetrahedral. Therefore, the easier this occurs, the more likely it is to occur, and that makes it more Lewis acidic. And this is where the p-pi bonding comes in. So the lone pairs on the 2p orbitals of a halogen, so in the case up here, fluorine, can donate into the empty 2p orbital of boron, which one here, and this stabilizes it. So it's almost extra bonding by putting the electrons from this filled one on the halogen to the empty one on the boron. And obviously this is only possible when it's in this planar configuration because of the way they have to overlap. So this stabilizes the trigonal planar structure and makes it less likely to react and therefore less Lewis acidic. However, this p-pi bonding is extremely distance sensitive. So if this was a chlorine here instead of a fluorine, it's much larger. It would be further away from the boron because of how big it is, and this p-pi bonding wouldn't be as strong. Therefore, the trigonal planar structure wouldn't be as stabilized, and therefore, it's easier, if we go back to point 2, easier to cause this geometry change. It's more likely to happen, and then it's more Lewis acidic. So it's all to do with the stabilizing effect of this p-pi bonding and how that differs with atomic radius. Now, the inert pair effect has come up a lot in these videos, so we saw it in each of them for group 13, 14, 15. There was a question about it at the end of the lecture 6 questions, and we also had a question about it in the discussion session. So I think it's a really important thing to be able to understand and get your head around. So we'll have one summary of it here, and these bullet points kind of answer the questions of what and why. So if you can understand the bullet points and the logic behind it and put it down, then you'll be able to answer any question on the inert pair effect. So first off, what is the inert pair effect? It's the tendency for the oxidation state too lower than the maximum to be more stable as a group is descended. So for example, we looked a lot at the group 14 oxides. They're a really nice example of it. So at the top of the group with carbon, it makes the oxide CO2, and carbon's in the +4 oxidation state there. And that's perfectly stable, perfectly wonderful. If we go to the bottom of the group and look at lead, when that makes an oxide, it only makes PbO. So lead is in the oxidation state too lower than the maximum, which is +2 rather than +4, because this is more stable. If lead was to try and make the oxide PbO2, it would be in the +4 oxidation state, which is really unstable, and it would be a hugely powerful oxidizing agent. So then the question is, why does this happen? Well, to achieve the maximum oxidation state in the group, all the valence electrons must get involved with bonding, and that includes this ns2 pair of electrons. So this pair of electrons in the valence s orbital have to get involved, or otherwise they become what is known as the inert pair. Now, since it's already a happy pair of electrons in a filled orbital, then to split it up is going to cost energy. And this is what I tried to show with the valence bond diagram before. So with the orbital hybridization, which can be used quite easily for groups 13 and 14 to explain it, for the s electron to go up into one of these sp3 hybridized orbitals, it costs energy. And the way that we make this energy cost, or this energy debt as I called it, the way we pay this off, is by the formation of new bonds. So forming bonds releases energy, and if it balances the books, then that can happen. So now we know how, what has to happen with the bonding to get to the maximum oxidation state. We can look at why this doesn't happen at the bottom of the group. So as I said, the way that we pay off the energy debt of splitting up the s2 electrons is by the formation of new bonds. But these new bonds have to be worth something, and that's their bond enthalpy, the energy released when they're formed. So at the bottom of the group, bond enthalpies are much lower, and therefore they don't pay off this energy debt. Like the energy that is given out by making these bonds in no way makes up for the energy it costs to split up the s electrons. So that's one reason why it doesn't happen. And the reason why the bond enthalpies are lower at the bottom of the group is that their orbitals are much larger, the atomic radius is much larger, therefore the orbitals don't overlap so well, and it's not such a strong bond. There's also a contribution from the poor shielding of the D and F orbitals, so that's the final bullet point, is that at the bottom of the group, the NS2 electrons have a higher effective nuclear charge than expected because of the poor shielding of D and F orbitals, so it actually costs more to split them up. So not only is the energy debt not paid off by the formation of new bonds, but the energy debt at the beginning, it costs more because they're they've got a higher charge, they're much harder to split up, so it takes more energy. And the reason for this is the poor shielding in the D and the F orbitals that obviously aren't present at the top of the group. So like with carbon, D and F orbitals haven't come in there yet, but they do lower down. And what happens is that very much like when we look at the Z effect, the effective nuclear charge in the first video, as we go across the period and therefore down a group as well, we're adding protons to the nucleus, so we're adding a positive charge. However, these D and F orbitals that should kind of screen this nuclear charge from the valence electrons, they don't contribute to this shielding effect. So when we go down a group, we've got loads more protons in the centre making a really strong positive charge, but nothing really shielding this positive charge from these s electrons we want to split up. So at the bottom of the group, there's almost a double whammy of why it's not going to happen, why we can't reach the maximum oxidation state. It's because this energy debt costs more, because it costs more to split up these pair of s electrons because of the higher effective nuclear charge, and also the way of paying it off through the creation of bonds just doesn't make up for it because the bond enthalpies are much lower at the bottom of the group. The final thing that I wanted to summarise was the use of enthalpy diagrams to see why some molecules or compounds are more stable than others. And we've already seen one question about it when we looked at the stability of phosphorus halides. And if you want to see a worked example of it in the book, they're on pages 1245 and 1246. Oh, I've written that completely wrong. 1245 to 1246. And this is almost exactly the same way as when we did it for the ionic solids. So we've seen lots of times like, why NaCl2 isn't stable as opposed to NaCl. And we can do exactly the same thing with these covalent compounds as well. So we can build up this Born-Haber cycle, and we just follow the arrows around, adding the terms, and following Hess's law essentially. There are a couple of differences. So when we were doing it for ionic solids, at the beginning we'd be forming an ion, so like either a cation or an anion. So we'd have terms for the ionization energy or the electron gain, and this time we don't have that. We just have the enthalpy of formation of a neutral atom of A or X. The stoichiometry is really important as well, so be careful to take into account that if you're reacting it with 3 equivalents of X, you've got to have 3 times the enthalpy change of formation for X. Now the other thing to think about is this term here, delta BEH. So this is the bond enthalpy of what's being formed, and the bond enthalpy can be thought of as the covalent bond equivalent of the lattice enthalpy that we used when we were looking at ionic structures. So it's essentially how strong a bond is the energy released when a bond is broken. It's much like the lattice enthalpy was the energy released when the solid was broken up into gaseous ions. And in the same way that as we formed something, the lattice energy was negative, in this case it's exactly the same. Like we're taking 2 independent atoms and putting them together to make the bond, and that means we use a negative bond enthalpy term. And the final thing is to make sure again, to pay close attention to the stoichiometry, especially for this final bond enthalpy term. So you said about why it's negative, but remember, for example, if we were using this to find PCl3, for example, the bond enthalpy is for a phosphorus-chlorine bond, like a PCl bond. Now in PCl3, we're making 3 PCl bonds, so make sure to keep the stoichiometry correct there.